All right, welcome. Today, we are going to pull back the curtain on a massive part of artificial intelligence called supervised learning. And trust me, it's the secret sauce behind a ton of the tech you use every single day, whether you realize it or not. Okay, let's jump right in. You know, everything we're about to talk about really boils down to one huge question. Can a machine actually learn from experience, kind of like we do? Well, as we're about to see, the answer is a definite yes, and we're going to explore exactly how that works.
So, where do we even begin? How in the world do you teach a machine to learn? The whole secret, it turns out, lies in showing it a whole bunch of examples from the past.
Let's make this super simple. Imagine you want a machine to guess if you're going to buy antivirus software this year. What would it do? It'd look at your history. Did you buy it last year, the year before that? Once it spots that pattern, it can make a really solid guess about what you'll do next. And that right there is the core idea, learning from old data to predict new outcomes.
Now, to put this all in context, take a look at this. Supervised learning is a huge piece of the machine learning puzzle, but you can see it's not the only piece. You've also got unsupervised learning and reinforcement learning. They're all fascinating, but for now, we're zeroing in on that first one, the supervised method. Okay, so what makes it supervised? Honestly, the best way to think about it is this. We're giving the machine a study guide that already has the answer key in the back.
And here's the more official definition. Supervised learning is all about training an algorithm on something called labeled data. That's just a fancy way of saying that every piece of info we give the machine is already tagged with the correct answer. The whole point is for the machine to figure out the connection between the questions and the answers so that later it can come up with those answers all by itself. This visual perfectly captures the two-step process. On the left, you've got the training phase. Think of this like studying with flashcards. The machine sees a problem and the correct answer over and over and over again. Then comes the testing phase on the right. This is the big exam. We give it totally new problems it's never seen to check if it actually learned the logic or if it just memorized the study guide. So what can you actually do with one of these models? Well, most of the time, their jobs fall into one of two buckets, either sorting things into different groups or predicting a very specific number.
And of course, these two jobs have their own technical names, classification and regression. Just about every supervised learning model out there is designed to do one of these two things. So let's break them down.
Okay, what's the real difference here? It all comes down to the kind of answer you're looking for. Classification is basically a sorter. Its job is to put things in neat little boxes. Is this email spam or not spam? Will this person click the ad? Yes or no? But regression, that's an estimator. It's not picking a category, it's predicting a number on a sliding scale, like the price of a house, tomorrow's temperature, or a stock price.
And here we go, two perfect examples. Over on the left, you've got a classic classification problem. Based on someone's age and salary, will they buy a product? The answer is either 1 for yes or 0 for no. It's one or the other. But on the right, that's a regression problem. Based on temperature and pressure, what's the wind speed going to be? The answer isn't a category, it's a specific number, like 15.7 miles per hour. See the difference? All right, so we get what these models do. But how does it all happen behind the scenes? What's the step-by-step process for actually training one of these things?
Well, it really boils down to a pretty straightforward 4-step playbook. First, you've got to collect all that labeled data we talked about. That's your raw material. Second, you split that data up. Third, you feed one part of it to your algorithm to actually train the model. And finally, you use the other part to test it and see how well it actually learned. And that second step, splitting the data, it is absolutely crucial. A really common way to do it is the 80-20 split. You use 80% of your data for training, and you save that other 20% for testing. Now, why do that? Because you have to test the model on data it has never seen before. It's the only way to know for sure if it's learned the real patterns or if it just got really good at memorizing the answers. The 80-20 rule is a great starting point because it gives the model plenty of data to learn from while still saving enough for a really tough final exam.
Okay, for our last section, let's zoom out a bit. Building one of these models isn't just about following a recipe. It's about making some really interesting strategic choices and facing some tough challenges.
See, when developers are building a model, they're constantly juggling these big questions. How complex should it be? If it's too simple, it'll miss important details. But if it's too complex, it might start seeing patterns that aren't even there. Then there's interpretability. Can we understand why it made a certain decision, or is it just a black box? And of course, you have to think about scalability and efficiency. Can it handle a mountain of data without taking weeks to process? These are the real-world trade-offs that go into building AI. And that leads us to one final big thought. That whole black box problem raises a huge question for all of us, especially as AI gets woven deeper into our lives. If a model can make stunningly accurate predictions, but we have absolutely no idea how it's reaching its conclusions, how much should we really trust it? Especially when the stakes are high. It's definitely something to think about.